video, we're going to talk about nuclear chemistry in order to prepare you for the Chem SAT. So, in nuclear chemistry, you're apparently responsible for different types of radioactivity and nuclear particles. You're responsible for the chemical reactions or nuclear reactions that go along with those emissions, and you're also responsible for half-life. So let's go through those. So, different types of particles you're responsible for. You're responsible for knowing what an alpha particle is, which is essentially a helium nucleus, which is why it's given the symbol 42He. 4 representing the mass number, again, number of protons and neutrons. 2 representing the atomic number, which is the number of protons, which is why it's identified as helium. You can also see it written as 4/2 with an alpha symbol. Those things mean the same thing. And they're essentially high-energy nuclei that are spontaneously emitted from the nucleus of an atom. So if it's losing protons, it's going to change its atomic number. And nuclear reactions result in something called transmutation. The element comes from one element to another after the radioactive decay. Another particle that can be emitted is a beta particle, which is an electron ejected from the nucleus, and which sounds kind of counterintuitive, but what it does is it basically takes a neutron, and when it gives off the beta particle, that neutron essentially becomes a proton, and your atomic number will actually increase. Positron is a positive electron. It's essentially the antimatter particle of an electron. It's going to have the exact opposite effect, and we'll go through a reaction with that. And the other main type you need to know about is called the gamma ray, which from our light unit, you know that that's just high energy radiation, but a lot of times that accompanies other types of radioactive decay. It doesn't actually change the mass number or the atomic number, but it does happen. It's an emission from radioactive elements. So let's take a look at a reaction of each of these 4 types you need to know. Alpha decay, again, helium nucleus, so it's got 2 protons. Your atomic number is going to drop off by 2 when that alpha particle is emitted. Now, since it had a mass number of 4, your mass number is going to go down by 4. Whenever you're balancing a nuclear reaction, you basically need to make sure that the top numbers add up to be the same thing on both sides, and the bottom numbers add up to be the same thing on both sides. Beta decay, it gives off an electron, like I said, from the nucleus, and the atomic number actually goes up by 1. Positron emission, it's the opposite, positive electron ejected. It essentially converts a proton to a neutron. Your atomic number goes down by 1. And then gamma radiation, again, it usually accompanies other types of radiation, but it doesn't actually lead to a change in the mass of the nuclei. Now, the other thing you need to know is half-life. So, a half-life is the time it takes for half of a radioactive sample to decay. So, just simply put, and again, you're not able to use a calculator on this, so you're not going to be given really hard numbers to work with. It'll probably be similar to this. If you have a 50-gram sample of a radioactive isotope with a half-life of 5 days, decaying for 20 days, how much is going to remain? So essentially, after each half-life, the mass of our sample that we start with is going to get cut in half. So if we're starting with 50 grams, after 1 half-life, again, we've determined that 4 half-lives are going to go by. After 1 half-life, or 5 days go by, you're going to be down to 25 grams. After another half-life goes by, or another 5 days, so we'd be 10 days into it at this point, you'd be at 12.5 grams. When the third half-life goes by, you're left with half of that. So after 15 days, you would have 6.25 grams. And then after the fourth and final of these half-lives, you would be left with 3.125 grams. So if you had this type of radioactive isotope and you started with 50 grams, 20 days later you'd only have 3.125, obviously sig figs would hate me on this, grams remaining. So you would reduce the amount of that radioactive isotope you have. Now, there are problems where you can go in the other direction, but essentially, anytime you're solving something like this, the first step you should do is figure out how many half-lives go by, and then go from there.